Good day, guys. I hope you guys are good. Today, we're going to be doing the bisection method, which is applied maths 2B, which is for engineering students and mathematical science students. So, it's bisection. The bisection method is section 2.1 in the textbook, which is numerical analysis. Okay. So how does the bisection method works? So with the bisection method, so basically with these methods now, I want to state that we basically looking for a root. So always remember guys, we're looking for a root with these methods now. We're looking for the exact root. Remember, for example, in maths, in high school mathematics, when we had like any function, so we usually know, let's say for instance, this was a 3 there. So this point will be a 0 and a 3 and 0, sorry, and then 3 and 0, this point there. So now, what are we doing now is we actually getting the actual, like we approximating the actual root. So the bisection method works this way. What we need is that we need a continuous function f of x. So our function must be continuous, that's number one. We need a closed interval. This is important, a closed interval, not an open, a closed interval. And then now we need to know that if we take, if we evaluate our endpoints of the interval with our function, and then they less than zero, meaning they negative, then that's what we also need. So f of a multiplied by f of b must be what? Negative. This is what it means. And then we also need the intermediate theorem, which is you guys did in maths 1b. Please go and revise that. So usually the intermediate value theorem says what? When we there's a number k in between f of a and f of b such that when you evaluate f of c is equals to that k, something like that. Please go and revise that. So now the question is, how do we find the root? So here's the algorithm on how the bisection method works. So we're going to be given, and what we need, remember what we need is a continuous function, you must check that, and a closed interval. So we're going to be given an initial interval AO and AB, which is just our interval AB. Nah? And then now we set k is equals to 1. You will see what k stands for in the next point, and process as follows. So now we're going to compute ck plus 1, which is the next term, which is the next iteration. We call this the iteration. So this is the next iteration. What is ck plus 1? Ck plus 1 is basically the midpoint of the, you're finding the midpoint of your given interval. So bk and ak basically stand, this bk, remember set k is equals to 1, so this is b1, and then this is a1. So this is your initial interval. So basically you're getting the midpoint of this initial interval. Sharp. You will see as we do examples. So basically this is the midpoint. Midpoint. Sharp. So now what they're saying now, remember after we get that in, remember our point, this number 3 point of saying f of a multiplied by f of b must be less than 0. So now you must be given an interval such that, so it's 1, for instance it's 1 and 2, né? This is our interval. They mean that, and we're given a function. So now f of 1 must either be positive or negative, né? And then f of 2, so if f of 1 is positive, then f of 2 must be negative for the bisection. This means what I'll show graphically what this means. Okay, sharp. So, and then step number 4, it says if f of k1, which is our next iteration, times f of bk is less than 0, and then now we move on. It means that it changed signs most. It's like the opposite sign, what I was trying to explain now, but you'll see as I draw the graphs. It's less than 0. We continue with our process and go on until we get, when we evaluate, we get now a what? A positive, and not like, for instance, if we evaluate our new interval, we get a positive, like positive sign. when you multiply them, then we stop. Okay, sharp. So then we update, meaning update k, we go on and go on and go on until you find such a case whereby we get f of a multiplied by f of b is greater than 0, which is positive. You'll see now. Okay, and then here we have the theorem that says let a1 b1 is equals to our interval, be the initial interval with f of, when we evaluate our interval with our function f, it's negative. And then now define so now this is the approximate root. So basically this is just the midpoint written in another form. So basically x of n, usually the textbooks uses pn, some textbooks use xn. So this is basically the midpoint of the interval. So remember, bisection method stands for midpoint. Then there exists a root p, which is what we are looking for. So we're looking for this root in this interval. So p lies in this interval, our root, such that this root minus our initial initial like approximation from the from our interval is less or equals to a half to the power of n multiplied by b minus a, which is greater than when n is greater than 1. Sorry about that. Okay, so there's the proof. I won't go through the proof. I just need to make sure that you guys understand how the bisection method works. So now in the next video, I think let's do examples, because at the moment you guys should be confused, which is fine, but then when you do an example, you'll see how it actually works. Sharp. Thank you guys.